Well, good afternoon, everyone. Thanks for joining our webinar on industrial heat pumps and the research that we have performed on how IHPs can be used in industry. So, Andrew, if you go to the next slide, please. So first off, I'd like to thank the team that worked on this, Paul Shining, Andrew Hoffmeister, Riaz Papar, who saw their names on the previous slide, but we'd also like to thank our sponsors from NYSERDA, Bonneville Power, Southern Company, and Tennessee Valley Authority. And with that, let me pitch it to Todd Amundsen, who is going to give a slight perspective on why this is important for utilities.
Hello, and thank you for giving me this opportunity. It's been exciting to be engaged in this ACEEE research effort for the past year, and well recognized that revitalizing industrial heat pump research, design, and deployments of high interest at industrial sites to help them reach sustainability goals with cost-effective technologies. Utilities across North America are interested too to help reduce greenhouse gas emissions, to help their industrial customers be more efficient and productive as well. The Pacific Northwest may be a bit unique with clean hydropower through the federal systems on the Columbia River and with the Pacific Northwest Power Act, but we too have a large and unique industrial load out here, and we see opportunities for deploying and supporting pilot projects here in the forthcoming year with interested industrial facilities. Thank you.
All right, super. Thanks, Todd, for that perspective from Bonneville Power Authority. I'll tell you a little bit about the industrial heat pump research that we've done, and of course, I'll note that the report is on ACEEE's website, was put up there last week. If you have questions as we go through this webinar, please enter those on the questions tab, the Q&A tab on Zoom, rather than in the direct chat. That'll allow us to be able to catch those and talk about those at the end of the webinar. So next slide, Andrew. So you might consider, why industrial heat pumps, and in particular, why now? Industrial heat pumps have been around for some period of time, but this is an opportunity really for a resurgence in industrial heat pump research, and in particular, deployment. Because of science-based targets companies are considering to reduce their energy and their greenhouse gases. Secondly, industrial heat pumps are a prime vehicle towards energy substitution, that is, in this case, beneficial electrification, where using electrons instead of fossil fuel-based fuels allows industries to pursue the path towards lower carbon directly. There also have been advancements in the space of industrial heat pumps. As you can see on the right, there's been new working fluids. New compressor innovations have come along as well. Compressors have been some of the issues in the past relative to reliability, but that's certainly something that with the new improvements provide a great opportunity for much greater reliability. There also are new options for heat-activated heat pumps, and Paul will talk about that here in just a couple of minutes. Additionally, there are other benefits other than straight energy reduction benefits, which you can also see here, such as improved control, speed of response, and the ability to deliver temperature accurately fairly quickly with industrial heat pumps versus, for example, steam-based systems. Next slide. I'll note it's also important because industry has a large footprint in the CO2 and greenhouse gas space, and also, of course, energy consumption. You can see in this slide that the CO2 emissions for industry, if you add both manufacturing plus other industrial, is some 22%. The slice for manufacturing, if you break it down, you can see that some of the major industries here, iron and steel, chemicals, paper, and food. And in fact, I'll highlight chemicals, paper, and food in particular, because as you'll hear in a couple of minutes, those are particularly of interest for industrial heat pumps due to the temperature ranges that they have. Next slide. So let me pass it here to Paul Shine, who's going to talk a little bit more about process heat and some of the details associated with industrial heat pumps.
Thanks, Ed. These two bar charts show the process heating demand by supply temperature and type of process heating need. So industrial heat pump technology is available for the lowest range, up to 80 degrees C, the dark blue shading, and partially for the gray area that goes from 80 to 150 C. New high temperature heat pumps are emerging in the market to supply up to around 160 C. And this will be explained later in the webinar by Gordon Orpicus. In terms of process heating use, fluid heating, distillation, and drying are the top types of process heating demands that an IHP can service. In our report, the 9 unit operations that we examined were either fluid heating, distillation, or drying. Next slide, please. So this slide, a little complicated, but let's walk through it. It illustrates the various types of industrial heat pumps that have been applied in industrial processes. First of all, you can design an industrial heat pump to be either closed, open, or semi-open cycle. Closed cycle, which we're more familiar with, which is what a residential heat pump would look like, has a heat exchanger on both the heat source and the heat sink to separate the heat pump working fluid from your heat source and sink. An open cycle is interesting in that you don't use heat exchanger at all. You use the process fluid itself, such as steam, would be compressed directly. And a semi-open is kind of in between the two, where you would have one heat exchanger that would be applied on either the heat source or the sink stream. So most of us are familiar with closed cycle mechanical vapor compression heat pumps, since they are applied in commercial residential applications. And they are found in industry up to around 80 degrees C currently. However, also industry uses what's called mechanical vapor recompression and thermal vapor recompression heat pumps. And most times they're not even called heat pumps. They're called MVRs or TVRs. And those have been fairly widely used in the food industry, chemical industry, paper industry. They're used for evaporation, processes, distillation, and drying. But our report examined the full range of IHP types shown here, even the heat-activated heat pumps, which are shown on the left. Those are pretty much, they're kind of in the minority, that haven't been applied too much, but they can either be prime heat driven or waste heat driven, which makes them kind of interesting. They don't use as much electricity, but you'll see the economics currently are not working as well for these type of heat pumps compared to the compression systems. Let's go to the next slide. So this is a simple diagram showing a heat pump. It's replacing out a steam boiler. So industrial heat pumps are like our home units, where we're pumping heat to a higher temperature, but they are generally at a much higher temperature. As I said before, they've been around 80 degrees C. Now they're getting up to 120, even hopefully to 160. They're a much greater capacity. They can be in the megawatt size, and they're usually very highly integrated into the industrial process, which makes them a little more complex. They're recapturing the recycling and boosting waste heat. And generally what you want to do is you want to find low lift applications. I'll use around less than 40 degrees C to maximize efficiency, because what you're trying to do is get the coefficient of performance of the COP generally to be greater than 3. And that's because you're using electricity to drive that heat pump, and you want to deal with the thermodynamics of a COP of greater than 3. In this case, in the diagram, we're showing a COP of 4. And that works out pretty good because we're replacing out that fossil fuel that has probably at best a combustion efficiency of 90%. And there's even more losses in delivering the steam and recovering it. So we're counting on that electricity to be produced with in a greener way. At a minimum, probably natural gas, hopefully with solar and hydro and wind in the future. And that makes it a more energy efficient and greener technology. Next slide, please. All right, so here we see the 9 unit operations we looked at that span across 3 sectors: paper, food, and chemicals. For 8 out of 9 unit operations, we had access to very detailed process hot and cold stream data that allowed us to perform what's called pinch analysis to identify the most optimum placement and size of the heat pump. So the process data that was available to us influenced the type of unit operations we selected, along with a lot of industry input of how they viewed to be the most ideal processes to potentially apply the IHPs. We created 2 levels of heat pumping in our analysis. One that we called economic, where we kept the IHP lift temperature to less than 40 degrees C. And we only usually focused on one heat source or sink stream to pump the heat. And then one we called technical, where we kind of really pushed the limit on the potential for heat pumping, where we're lifting up to 70 degrees C and utilizing multiple heat sources and sinks, where we're expecting that the company, if they were going to do this, they would really do a lot of process analysis and really revamp their process. We do think our results are realistic and perhaps even conservative, because the input we receive from programs in other countries that the opportunities of completely eliminating steam usage for a unit operation, you would eliminate not only the combustion efficiency losses, but also the losses associated with delivering the steam to the process and recovering that steam and bringing it back to the boiler. And we didn't take that into account, so we feel that that is conservative. Okay, so the next slide. Here we show what we call tornado plots. And in our tornado plots, we are examining the 6 types of IHPs that we analyzed, and the 3 compression types, the 2 heat activated, and the thermal vapor recompression. Of course, all the IHPs save natural gas, the red shaded areas, and depending on the heat pump coefficient of performance, will dictate how much natural gas we save. However, we took into account the electricity demand to drive each heat pump, and that is the green shaded area of the CO2 emissions that are attributable to the electricity. Okay, so, but the net CO2 savings was positive. They all saved CO2, just greater or lesser amounts. Although not reflected in this slide, the report did look into the effect of the heat pump types for each unit operation and sector as the electrical grid in the United States gets greener from 2020 to 2050, and thus producing less CO2 per kilowatt hour. Okay, I think that completes my slides. I'm going to hand it back to you, Ed, I believe.
All right, next slide. So thanks, Paul. As you can see on the left-hand side, what we did is we added up the impact for those 9 unit operations that Paul had talked about for the different sectors for food, paper, and chemicals. And you can see that combined across those 9 unit operations, the amount of energy saved or avoided could be the equivalent of some 3 million homes. The energy provided to of course, power those 3 million homes. Similarly, if you look at the amount of CO2 that's avoided, they could approach about that of 5.4 million cars. Now, this is just for the 9-unit operations in the cases that we had looked at. As you look across more unit operations and a broader breadth of industry, not just these 3 industrial groups, but many more, that impact, of course, could greatly increase. The other thing that could increase is that as the electricity provided by the grid becomes greener, the amount of savings from the CO2 perspective will increase. And that's because of the fact that the reductions, as Paul showed in the tornado plots, for the CO2 were far greater for this reduction from natural gas than it was the increase from electricity. Next slide, Andrew. Well, one of the challenges that this research uncovered was the electricity to the natural gas price ratio. And that is, in certain states in the US, this ratio is relatively high, and the price of electricity then is fairly high. That presents a challenge for the use of electricity for any application in industry. But you can see that there are a number of states where today that ratio is fairly low, such as in Washington State, for example. New York is another candidate. Ohio, you can see that kind of the real dark blue at this case. So there's an opportunity here, not only for policy to make a difference, but also utilities can make a difference here relative to programs that they have to incentivize the use of electric technologies through the use of rates that allow industry to tap into these technologies. This price gap is particularly important to accelerate adoption where that ratio is greater than 4. In this case, which you can see on the map, is in a fair number of states. Next slide. So some of the other work that we found, looking at the paybacks, this is the simple payback in terms of how quickly it would take to recover the cost of the industrial heat pumps. You can see on the left-hand side that there's a number of cases where the payback is less than 2 years. Looking at the legend, you can see that's when the gas price is 3, 5-ish, and upwards of 10. And this varies for the different types of heat pumps that Paul talked about, the MVC case, the MVC semi-open, or the MVC all the way open case. The reason why there's a difference is the presence of heat exchangers. So the MVC case has 2 heat exchangers, the semi-open has 1 heat exchanger, and the open has none. That affects, of course, the economics and the payback. What you can also see is that as the electricity and natural gas price ratio increases above 4, as you can see on the right-hand side of the plot on the left, that payback increases significantly above 2 years. Now, 2 years as a common target within industry for acceptability, at least gets you on the radar screen. So one of the things that we did on the right-hand side is we looked at what that economic gap is. This shows that that gap can vary, of course, with the price of gas, but you can see that it varies between 22 and some 60%. And this type of range for the different types of heat pumps, again, the MVC and the MVC semi and the open case, allows you to see what it would look like to design incentives for this case to push the adoption of industrial heat pumps. And this is something, of course, that will be good for discussion with policymakers and utilities and others that are looking to push this. Of course, I'll also note that where the electricity comes from is also important. If you were to electrify using grid-based electricity in some parts of the US at this point, actually emissions could not go down, but could go up if industry went gonzo at this point on electrification. So that's why we use the word beneficial electrification. Beneficial is where the electricity being provided is of low carbon source. So also in that graph showing the map of the states, in those states where it's low, such as Washington State, New York, there's a fair amount of hydro, and that helps that electricity then is already fairly green. Next slide. So I mentioned policy just a bit there, and you can see that economic incentives for IHP adoption could be particularly important to accelerate not only electrification, but the reduction in energy and greenhouse gases associated with the use of industrial heat pumps. It's also important to push pilots and demonstrations. Demonstrations and pilots are being pushed in other areas of the world, as Gordon Arpagus will mention in a few minutes. And it's also important to support the growth of a domestic supply chain for the industrial heat pumps, as well as the service capabilities to ensure that the heat pumps are maintained, are implemented, and are interfaced as best as possible. Finally, I'll note that it's important for training of a skilled and diverse workforce in this space. This is an opportunity for the low carbon future, for the workforce to come along and be prepared to support this and other type of electric technologies. The graphs on the right, the illustration on the right, summarizes the opportunities there for policy-related enablers in several different areas, which I just mentioned on the left-hand side. Next slide, please. So to summarize, IHPs can save up to 32% of the source energy for process heat. Process heat accounts for more than 50% of the energy use in the industry. So it's really important to go after process heat with opportunities that will lower energy and greenhouse gases. The amount of savings just from the 9 unit operations that we looked at in those 3 industrial groups could account for the energy associated with powering 1.4 million homes, or the emissions for CO2 of some 2.7 million automobiles. IHPs can have paybacks that are within the range of acceptability for industry, particularly where the electricity to natural gas price is favorable. But there are some uncertainties in this space. That's where policy incentives can certainly be useful to help adoption and to address areas in the country where those paybacks are greater than the 2 years. Field level pilots are particularly important in this case to not only demonstrate IHPs in multiple applications other than the 9 applications that we showed in this report, and also to engage a broader user community. Next slide. I'll note the call to action. Pilots and demonstrations, again, are particularly important areas to demonstrate support for. RD&D needs to be revitalized in the US, and that's an area where the user community can be engaged. It's important as well to push practical education, that is helping folks to understand the evaluation of process heat and where industrial heat pumps can be most effective. Those are the pinch analyses that Paul had talked about. International collaboration, also really important to revitalize there as well. And I mentioned workforce, and also important, again, to provide policies that will help to accelerate adoption. With that, let me turn it over to Gordon Arpagus. We're really glad to have him provide international perspective here. Next slide.
Hello, everybody. Ed, can you hear me well?
Yes, thanks, Gordon, and thanks for
super.
joining us
Yeah.
late.
Thank you. So I'm Gordon Arpagus. I'm from Switzerland at the Eastern Switzerland University of Applied Sciences, and would like to give you a short overview on the market of industrial heat pumps, especially in Europe. Next slide, please. This slide shows the temperature ranges that industrial heat pumps are heading towards. So towards higher temperatures. On the left, you see the supply temperature, which goes up to 160 degrees. And on the bottom of the x-axis is the source temperature for the heat pump. So if we are at around 100 degrees, we speak about high temperature heat pumps. So it's a relative term, but at 100 degrees, it's possible to generate steam, and this offers many more applications. And in blue and in red, you can see two examples of industrial heat pumps, which is the first one is from Kobelco. It's from Japan, which can reach 165 degrees. And another is from Ochsner. It's an Austrian company, also providing high temperature heat up to 130. On the right, you see the classification. I think Paul showed it already before. So it's mainly focusing on closed cycle heat pumps and electrical driven compression heat pumps. Next slide, please. Literature shows that that there is a high research activity, especially in steam generating heat pumps. So that's for sure a highly active research area, especially to generate low pressure steam, so at around 120, 130 degrees. And here there are applications, but there is a lack of compressor manufacturers and available compressor products. So that is main research activity in this field. Next slide. This slide shows a variety of products which are available on the market. So you see on the left a graph on the y-axis the maximum heat supply temperature, and this as a function of the heating capacity of the heat pump. It's in logarithmic scale. So in the middle there is 1000 kilowatts, so 1 megawatt. And in color there are different compressor types. So yellow is a piston compressor, blue screw, and red turbo compressors. And there are the brand names listed in this graph. And you can see that it goes up to 165 degrees. And this is actually a status from 2018. So in the last 2-3 years, this list has further developed. But it shows that in principle, high temperature heat pumps are available on the market, especially European companies are active there, and also some companies from Japan. On the right, you see some pictures of such heat pumps, industrial scale, typically installed in a machine room. They look like a container, which makes heat and cold. What you also can see in the middle of the slide are the refrigerants which are used in the different heat pump products. And the refrigerant is the working fluid which is inside, which is evaporated, compressed, condensed, and expanded. And you can see that there are these numbers from ACEEE and so on. So R245FA, for example, is a hydrofluor carbon, which has quite a high global warming potential, close to 1000 times of CO2. And that means it needs to be replaced in the future due to regulations. And that's an active research area also, these refrigerants and the alternatives for these refrigerants. Next slide, please. On that slide, you see a table from some case studies, and it shows a little bit the variety of applications. Here are case studies from the company Ochsner from Austria. So you see here the heating capacity, which is several hundred kilowatts. Then the application in, for example, district heating, then hot water production, but also heating and cooling using both sides of the heat pump. Then for sure heat recovery applications and some other heating and cooling applications. The temperatures of the heatsink are here higher than 80 degrees, 90, 120 degrees. So these are installed case studies in the field. And the heat sources are here around 45, 55 degrees. What you also can see is the screw, the compressor type, which is here all screw, which is the key technology of these heat pumps from Ochsner. The COPs which are achieved are depending on the temperature conditions, but you can see it goes up to 4.0, 4.2 if the temperature lift is not too high. Next slide, please. On that slide, you can see the status in Japan, and these are all commercialized systems from different companies like Maekawa, Kobelco, or Mitsubishi, or Fuji Electric. And here again, you see the technical parameters of these heat pumps. And what you can recognize is these systems are on the market already more than 10 years. So mainly in the domestic market in Japan. And yeah, it will be interesting to see if they are also able to export their systems to other countries. And what you also can see are, for example, the cycle type. So if you're a little bit familiar with the heat pump design, that's the lowest row. You see transcritical or subcritical. So transcritical is a cycle where the refrigerant, in this case, there for Maekawa, it's CO2, so a natural refrigerant. It's operating in transcritical conditions. That means that it is very suitable for processes to heat up a stream, so for heating up processes. Yeah, next slide, please. Here, another slide I would like to show you, because this shows systems which are large scale. So these systems can provide more than 1 megawatt of heating capacity, and many even more than 10 megawatt. So these are systems which are used in district heating applications, but also in industrial applications. So the first one is Friotherm, is from Switzerland actually, can produce steam of 137 degrees, 25 megawatt. Typically these are tailor-made systems and customer-specific designs. Then Turboden from Italy also provides large-scale heat pumps. They are strong in ORC. Then we have MAN, it's also from Switzerland, and they have a CO2 heat pump, a special compressor, which provides very large or high capacities. Mitsubishi from Japan, we have seen before already. Then Siemens is from Germany. They are providing very large heat pumps up to 70 megawatt, according to their website. And also they have first reference cases, especially in Germany. Then Ochsner we have seen before, and Kobelco. Last slide, please. So I'd like to sum up a little bit the main key findings from the market view. We have seen before also from Ed that the price ratio is very important. So the electricity to gas price ratio is a parameter of market attractiveness. The applications are clear. So hot water, hot air, steam, these are the main carriers, energy carriers. Then we have various application cases. We could go here even more in detail in other presentations. And there are several heat pump products available, and also technologies from various manufacturers. But this market is really at the start. So it's really starting, or this market diffusion is just at the beginning. Steam generation, heat pump, these are I think very important technologies, especially to produce low pressure steam. Then many more applications will be possible. Here you see a COP value of 3.2 at 62 Kelvin temperature lift. That's an average value which can be assumed quite reasonable. So from many suppliers. Then the cycles can vary. The technologies we have seen, large scale heat pumps are available. Then heat pump integration, that's typically case by case, depending on the situation, which means that process engineers are needed to do this integration. From research perspective, there is quite a worldwide activity in different countries. You see here some countries. Then last but not least, the topic of refrigerants. So there is a trend towards natural refrigerants like hydrocarbons, yes, and CO2, water, so it means steam and ammonia, but also synthetic refrigerants like these HFOs, hydrofluorolefins, which have very low global warming potential. Thank you. That's, I think, all from my side. Last slide, maybe. Okay, so I'd like to just to acknowledge some projects in Switzerland. Sweet, for example, that's a larger project where we are focusing on decarbonization of Switzerland. Thank you very much.
Okay, well, Gordon, thanks so much for joining us. We realize that it's late in the evening there in Europe, so particularly appreciate you joining us to provide the international perspective. Next, we'd like to bring up Colin McMillan from NREL to talk about applications as he's been looking at process heat. But Colin?
Right. Thanks, Ed. Let's see here. Right. So I'm Colin McMillan with the National Renewable Energy Lab. Happy to join in on today's webinar. It's always exciting to talk about industrial heat pumps. I just wanted to give a very short overview of some of the work that NREL has been involved in with characterizing industrial process heat demands. Some of this was already mentioned in Paul's work, if you caught that in the presentation. But so prior to these efforts, really the only existing work provided just a little bit of disaggregation of some low temperature demands in the industry, and there was some analysis on some thermal demands in the most energy intensive industries. So this work that I'll be summarizing today was really part of a larger push to get better estimates of industrial energy data together, better in terms of the operational, geographical, and temporal resolution. And we hope to use these data to improve analysis and modeling for the industrial sector. Right, so we move on to the next slide. Right, so the first thing that we did with this improved characterization is to break out energy demand by process heat temperatures. And so when you do this, you can get this temperature demand curve as you see in the figure. So what this does is it shows cumulative energy demand as a function of temperature. And in the figure, it's also broken down in terms of general end use categories. So those three categories are combined heat and power and cogeneration processes, conventional boiler use, and process heating, which in this case is you can think of those sort of direct fired process heat equipment like kilns, furnaces, and ovens. So when you add those three end use curves up, you get the total curve at the top there. But just wanted to highlight two big observations that came out of this work was that one, at least in the United States, there's a lot of low to mid temperature process demand. So at least 2/3 of all industrial process heat process heat from the combustion side, is used for process temperatures at or below 300 degrees Celsius. And a related point is that there's a lot of energy that's used to heat water. So if you look at those individual end use curves, you see that boilers and combined heat and power account for about 90% of that 300 degrees C and below. And so these two related facets describe at a pretty high level what a big opportunity exists for process heat in this temperature range. Of course, for this work, it would also be, and for this work and also thinking about industrial heat pumps, it would also be nice to have the waste heat temperatures included here, but that's something that hasn't been done yet at scale. There is some existing research that looks at characterizing waste heat on just sort of a general industry scale for the United States. All right, next slide. All right, so the next thing that we did was to disaggregate these process heat demands geographically. So the idea here is that because many industries may be geographically concentrated and those industries have different process heat demands, this means that those process heat temperature demands might also be geographically concentrated or have some sort of potential pattern in their distribution. And as Ed mentioned before about the aspect of beneficial electrification, this sort of disaggregation geographically is important when you are looking at those process heating electro technologies and want to dive into larger implications for interactions with the grid, as well as emissions implications of electrifying what was previously combustion heat. Also say that this sort of geographical disaggregation is also important for other sources of renewable energy, as well as alternative sources of process heat. So each of these figures is a map of the United States, continental contiguous United States, broken out into counties. The darker blue colors represent more process heat energy being used in that county. The top right figure, we'll start there. This shows all process heat demands across the United States. You can see that there's some concentration around Chicago and Northwest Indiana, where there's still a lot of iron and steel production. Of course, down in the Gulf, you have a lot of chemicals industries as well. If you go down to the figure in the lower left corner, you have the process heat demands between 80 and 150 degrees Celsius. You can see like the total process heat demands, those are pretty well dispersed throughout the country. There's still this sort of middle slice in the plains down through Texas, where there's really no process heat demands. I think that's largely agricultural areas. And then if you look in the bottom right corner, you see process heat demands at the very high end of the spectrum. So these are 1100 degrees C and above. And you can see from the map that those are not as widely distributed as some of the lower temperatures. So to sort of tie everything together, these low temperature demands are really a big piece of the energy pie for industry. They are representative of a wide variety of industries. And because of that, they are also quite geographically dispersed throughout the country. So I think those are sort of interesting and important considerations to think about when thinking more actively about how to further industrial heat pump development and adoption. Certainly how to accelerate those. So if we go to the last slide, just a quick wrap up. So this characterization of industrial process heat is sort of an ongoing process, and there's certainly a lot more work that is left to be done. But I think that's my whirlwind tour.
Okay, super. Thanks, Colin. Really appreciate your perspective there. So certainly where the process heat is matters, and where it is relative to the ability to deliver. Low carbon electricity is also important, which is something that we can see from your illustrations. And looking back to the work that Corton mentioned, certainly there's a lot of work going on in the international scene. Europe, Japan, Australia, as a matter of fact, seem to be particularly advancing very quickly relative to industrial heat pumps and industrial applications. Corton showed the scale of those types of applications, which is maybe upwards of 50 megawatts potentially, but definitely some large scale demos in the multi-megawatt scale at present. So turning at this point to a few questions, I wanted to spark a little bit of discussion here with our panelists. First question I'll highlight is, what applications look best for industrial heat pumps? The work that Paul showed suggested that based on the range of process heat available, as far as the temperature range, chemicals, pulp and paper, and food look like likely candidates. Those are the ones that we studied. Any discussion there on other applications or the suitability within those industrial groups?
Want me to take that, Ed?
Sure.
Okay. Well, any applications in the food industry and maybe the chemical industry where there's dual heating and cooling is a big area that we actually didn't dive into in our report, but we knew that was a fantastic opportunity because you're kind of doing double duty there, and the economics of the heat pump, again, being a refrigeration system and a heating system, will look very nice for many applications. One thing we didn't mention is we kind of uncovered, we think there's a tremendous opportunity in the ethanol industry. And that's one of our 9 case studies. It actually showed a very large amount of savings, and it's an area that we would like to dig a little deeper with the ethanol industry, especially the dry mill process. And also distillation needs further examination, since that's widely used in the chemical and petroleum refining sector. You know, we didn't really even, we didn't dive into the petroleum sector, but we know there's opportunity there too.
Right, because the petroleum refining sector has a lot of similar unit operations to those found in chemicals. But across all 3 of those industrial groups, there's similar types of operations. Evaporation, drying, for example, seem to be something that's found across a pretty broad stretch of industry. Mm-hmm. Anybody else want to mention on applicability? If not, let me hit up another question here, and that is, folks raised the question of fossil fuels versus renewable energy, and how electrification will help to reduce not only energy, but greenhouse gases. So I'll start on that, saying that as the grid becomes greener, the use of electricity itself will become greener. That's the indirect pathway. There's also a direct pathway, and that is where industry could use renewable electricity directly. That's a way to spur electrification and to lower the greenhouse gases directly as well. Any other comments on that? If not, I'll go on to the next one, and that is learning curves. And Corton, I'll pitch this one in your direction. The question is how much we might expect the cost for industrial heat pumps to come down as industry learns better how to not only use the industrial heat pumps as far as integration, but as the industrial heat pumps become more efficient themselves. Have you seen any information on learning curves and how that might decrease the cost of industrial heat pumps?
Yes, I think the learning curve is very much depending on the competition. So if there are more suppliers, then there is more competition in the offers, and that for sure is a main driver. And then it's not only about the equipment cost of the heat pump, it's a whole project, and the heat pump is maybe just 30% or less of the whole project. So it includes also installation of further piping and integration, maybe some storage tanks. So we have to consider the whole project budget.
Yeah, that points out the integration piece, which was the topic of perhaps a couple of other questions. One I'll pitch to Paul there. There was a question about how the data was obtained for this work for the pinch analyses and how that deals with the integration. I'll start that out saying that we got this information from Chalmers University on processes that were integrated at the time. But the way that the analysis could be improved would be to use data for an individual facility that's already integrated or to simulate further integration. Paul, you want to take it from there?
Sure. Yeah, we, as Ed mentioned, we were fortunate enough to get data from the Swedish firm called Chalmers ETA, and that was pinch data, which really means it's a series of heating and cooling, temperature and enthalpy data streams that are integrated into an overall process. And we took that and performed pinch analysis. And the benefit of, there was another question that was asked in the chat of like, if we had not used pinch analysis, would the answers come out differently? And the answer is yes. Would the advantage of the pinch analysis, which I would encourage any industrial plant that has a lot of heating and cooling streams to do this, to make this extra effort, is that what you're really doing is you're finding the optimum placement of the heat pump in the process. You want to pump heat around what's called the pinch point. And if you don't do that, you may end up lifting the heat or having to lift the heat over a higher temperature range, and therefore the economics won't be as good. And also you're sizing the heat pump properly. You maybe would oversize it if you didn't use the pinch analysis.
Okay, another question looking at the chat deals with the reasons for the variation in the electric to natural gas price ratio in the US. So I'll start on that, and then maybe Colin, you have some perspective on that as well. It depends on the sources of energy in those various locations. For example, in the Pacific Northwest, relatively low cost of electricity due to high prevalence of hydro. There, New York State, a few other places in the Northeast share that similarly. The availability of natural gas also has some influence there, but largely we think it's the price of electricity that has a stronger influence there. Colin, any additional perspective there?
Yeah, I mean, just to add there might be sort of layers of detail on those electricity rates based on the market that different facilities are in. I think it's probably also worth mentioning that companies might, I guess, getting down to the company level, companies might have fuel contracts with suppliers, and so those, I don't think those prices really show up in data that are reported by the Energy Information Administration. So if you're looking at getting down to those issues of adoption and configurational considerations, that's one additional consideration for prices.
Okay, great. Another one that I think, Gordon, we could use your help on as far as the question deals with working fluids and the compatibility of the working fluids with the materials in the IHPs. And I think the folks in Europe, maybe Japan, have been working on that. Certainly with the working fluids, it's important to get the greenhouse gas warming potential down and the efficiency up, but also there's compatibility issues. Have you seen any research in that area that you would comment on?
Yes, so replacement of existing hydrofluorocarbons, that's like needed. It is pushed by regulation, and And so these are all activities, which are very pushed now. And especially in the US, you have some suppliers of synthetic refrigerants. So I can imagine this is quite an important market. And so I think now the replacement fluids are clear. It's clear which ones would be the ones, and it's just a question of time when these are introduced in different applications of heat pumps, depending on the temperature levels and so on. And then there is all this testing with the materials, with the plastics, elastomers, with the metals, steel, copper, and so on. Long-term tests, high temperature tests, and corrosion tests, and all this. This is like standard procedure.
Okay, yeah, thanks, Gordon. It really is great to have the perspective of where things are the most advanced at this point, which is in probably in Europe and Japan, and probably another one that heads that direction. There was a question about the capacity of the suppliers to meet demand. For example, if demand for industrial heat pumps accelerates greatly, will the suppliers be able to keep up with the industrial demand in this case? Certainly, we've seen a demand increase for residential and commercial residential heat pumps. Any perspectives on the ability of the industrial heat pump suppliers to meet demand? Any thoughts there?
Yes, I think very good question. So the market is pulling, how do you say? Yeah, pulling, and the technology is pushing. So, and we need to have many engineers now to really do the planning and also producing these heat pumps. So it's there are ambitious goals, and if you look at the numbers, so heat pumps will be very much a key technology, and the numbers will almost explode in the next years. It will triple in 10 years, or it's really some interesting market.
I have a question. Could I ask Gordon a question? Because I think we have an experiment in Europe now with the natural gas prices probably doubling in the last 1 or 2 months, right? With the Ukrainian. How are you seeing our end users now? Have they ratcheted up their interest in industrial heat pumps in Europe, or is it not quite hit?
Yes, I can just say that last week there was this high temperature heat pump symposium in Denmark. Also some American participants were there, and we can really see that the need is there. So it's much higher growth and many more suppliers in this market. And the gas price situation with the war in Ukraine is pushing towards electrification, as sad as it sounds. But for the climate, maybe it could be an additional push. And so we'll see how this develops.
Yeah, that's a good point. The strengthening of the drivers is definitely something that we see on the horizon here. Many other questions, I guess, in the chat. Sorry, we aren't able to get to all those because we're out of time, but I'd encourage you, to reach out to us for additional questions. We see that the pilots is an area that in particular we're pushing. That's the next phase of our research. So if you have questions there, feel free to reach out to us. Secondly, I'd encourage you to look at the report because there are more details in the report, and we also have an annex there with lots of details as well. So with that, really appreciate the interest, the attention, and look forward to working and talking with many of you in the journey with industrial heat pumps. So thanks again for all the participants and the folks that joined us on the panel.